Welcome. This has been a long time coming, but this is a completion. The remaining notes for my 312 Chemistry 312 lecture. Last year, when COVID finally hit, shut down, and I switched all online and had virtual lectures, which I have since posted on YouTube. Well, the first half of the class never got recorded because we were all in person at the time. Here are the missing lectures, starting with Chapter 10, Alcohols. So starting off with just a functional group, alcohol. How do we end up classifying? We can classify alcohols, primary, secondary, and tertiary alcohols, as well as phenols. When we classify an alcohol, it's based on how many carbons are attached to the alcohol carbon, meaning like in a primary. So let's look primary, secondary, tertiary. In a primary, we have only one carbon attached to the alcohol carbon. Secondary, we have 2 carbons. And the tertiary is, of course, 3 carbons. It's essentially looking at a way of looking at how many H's are attached to this alcohol. How many H's are attached to the carbon attachment. And of course, phenol is our benzyl alcohol. Because these guys are going to react in various different ways. Looking at these guys, these are our basic. Now, one of the things we need to worry about is how do we name these guys? How do we name these guys? For one, when we name these guys, we will lose the E ending, and it will switch to an OL ending. So butane will become butanol. Cyclohexane would be cyclohexanol. And when we number these to number where the alcohol is, we will number favoring the chain starting with alcohol, trying to make alcohol the lowest number. Because OH as a functional group takes a higher priority over alkenes and alkynes, which take a greater priority over halogens. But from there, we will just name and number these as usual. And when we number these guys, the number goes before the OL. So, for example, if we had a choice of like, okay, I've got 1, 2, 3. That'd be 1 propene, 1 all. 1 propene, 1 all. So put a number between the ending of the EN or YN or AN and the OL to specify where that's at. If there's no other functional group, you could just call that 1 propane and all. Now, if OH, for whatever reason, is part of a substituent, meaning like, oh, we have something more important than the hydroxy, which we'll get to that, like aldehydes, ketones, and whatnot, then we call this hydroxy, a functional group, hydroxy. So if, for example, let's see, That's a ketone. Ketones take more precedence. So this is going to be a 2-butanone, but that's going to be 4-hydroxy, 2-butanone. 4-hydroxy 2-butanone. So we have to put them in the proper place. Now, when we look at priorities of naming, acids are going to be the highest, followed by esters and other acid derivatives, followed by aldehydes, ketones, alcohols, amines, alkenes, and alkynes. Then we get to our alkanes. Finally, we have ethers and halides. I'm going to just leave it as an X. Ethers and halides. So alkanes are probably going to favor most of the things, but when we have alcohol, is going to be reasonably high up there, but when we get double bonds with carbon, with oxygen involved, those are going to be higher still. When we have two alcohols on a, when we have two alcohols in a compound, we call this diol. And we'll have to name this and number this depending on where the alcohols are at. So right now, there's 1, 2, 3, 4, 5. So it's a it's a pentane diol, but we'd call that, so 2, 4 pentane diol. Pentane diol. If, say, this is part of a big group, or you could say pentane 2,4-diol. However, if the alcohols are on the same carbon, you can call that if they are vicinal to each other, right next to each other, we can call that a glycol. Now, there's also some phenols that we can work with. Some of them are common enough that they have a fancy name. If it's just one alcohol, it's a phenol. If we have a toluene group, it becomes a cresol. So this one is ortho cresol, but you could just call that hydroxytoluene, ortho-hydroxytoluene. A diol on the, depending on where they're at on the phenyl group, has different names, like 1,2 benzene diol is called a catechol. A 1,3 is called sorcinol. And a 1,4 is a hydroxyquinone. Hydroxyquinone. Those are the fancy names for essentially these guys that you could probably name other ways. Okay, so let's look at some properties. What does having an alcohol do for this? The boiling point will be much, much higher. Both alcohols and ethers will have a very large dipole, but the boiling point of alcohols are extremely high because of the hydrogen bonding, this intermolecular force that we learned about in general chemistry. Now remember that hydrogen bonding is incredibly powerful, so much so that if you just looked at, say, something of the exact same weight as like propane. Propane has very similar weight to, say, ethanol, but propane is a gas. Ethanol can remain liquid for quite a while before boiling away because the hydrogen bonding creates such strong force. Now, this also has effect on solubility. We're going to have various regions of hydrophobic and hydrophilic polarity on a organic alcohol, especially depending on how big they are. At low weight, alcohol is perfectly miscible in water in all amounts. Like methanol and ethanol can dissolve infinitely in water to the point where water ceases to be the solvent and becomes the solute. They can be mixed together in all quantities. Wood alcohol, basically, yeah, the wood alcohol, methanol, grain alcohol, and rubbing alcohol, propanol mixed together. In fact, they will form an azeotrope, meaning that you're going to have a mixture, say 95 to 5 of these guys mixed together, water and alcohol, so you can't really ever get it 100% pure in there. Now, you might see something like absolute alcohol, where it's like essentially pure alcohol, versus denatured alcohol, where we've maybe added stuff to it to avoid drinking it. So there's various different types of alcohol, depending on what you're looking for. 95% pure, because of the azeotrope. Absolute alcohol, where it's made in the absence of water and you've tried to keep it out. Now, alcohol has some interesting properties that we didn't really think about before. It's acidic, very, very weakly acidic, but it's acidic nonetheless, so that an alcohol in a strong enough base, a base stronger than OH, can form an alkoxide. Alkoxide, RO minus. Now, this alkoxide can be stabilized with various electron withdrawing groups. Basically, the O doesn't really like to have that negative charge. It can have it, but if, for example, if I had CF3OH, this is going to be a particularly more acidic hydrogen than, say, methanol. It's going to, a weaker base could pull that away, because what happens? You have that carbon, you have the oxygen with the lone pairs, and you have the F's pulling electron density away toward, so it's going to stabilize that. Yeah. Now, there's often can often do this, form alkoxide, by using a metallic base, depending on what you want. You can use a base, a metal base, we're going to call like M, plus our ROH and you can form RO minus, metal cation, and a half mole of hydrogen gas. This is one way to keep this from reversing. The metal base oxidizes, thus reducing hydrogen, and the hydrogen escapes. Once that escapes, well, you can't get this to go backwards. If we're looking at this, sodium is 1, but it's weaker than, say, potassium for this, but it's weaker than a sodium hydride. But this is in a special THF solvent. THF, if you don't remember, is tetrahydrofuran, a common solvent of a 5-membered ether ring. Now, depending on what type of alcohol you have, depends on which of these guys will react. That primary and secondary will react with sodium. With sodium, well, we react with all of them, but sodium, potassium, sodium hydride. Oh, sorry, that's just, my bad. Not primary and secondary, but primary and methanol. Methanol will react with all of them. They're overly reactive. Secondary and tertiary will react with K, with our potassium and our sodium hydride. But very stubborn compounds will need this guy. Good for particularly stubborn ones. So not all secondary or tertiary will react with potassium alone. Obviously, you want to use probably the safest and the cheapest ones, so you don't need to overkill this with potassium every time. So now, phenols are actually way easier to acidify. They're naturally acidic, and that's because they become resonance stabilized. Like if you just put this with hydroxide, they will naturally break down. In fact, we have a Ka of this, but what it's going to happen, it's going to form, well, obviously O minus, but it's also going to be able to switch this resonance around by forming, so these various, put the negative there, and we can also look at these various structures. There, and there. So all of these resonance stabilize your structure, thus making this significantly more acidic. That's where we're going to stop for now. I'll pick this back up with alcohol synthesis and other reactions. Thank you for your time.